Hello everyone and welcome back to Particles in a Box. Today we are talking about series, limits, and derivatives again. We're doing the follow-up to the previous episode where we go over some example problems. As part of my quest to make these videos not an hour and 45 minutes long, I'm going to try splitting up the theoretical part and like the super basic examples to some more complex examples and our example problems. I don't have a ton of examples for these again, simply because, again, if you want a lot of practice, right, taking a calculus class is going to be your best way to do it. And there are plenty of examples, and like you can look up a derivative worksheet and you can just like take derivatives for an hour if you wanted to. But I don't want to do derivatives for an hour as much as I like math and physics. So that being said, let's get into some example problems. So first up, we'll do some example problems with limits. So if you go back to the previous episode, right, where we talked about limits, right, I didn't really explain, well, how do we evaluate limits? I mean, sometimes, right, you can just plug in the value, right? If it's a well-behaved function, right, you can just plug in the value and it'll give you the limit, right? Sometimes that isn't always the case. So you do have to be careful. But for example, if you want the sine of ax over x, and what the limit is x goes to 0, right? There's a hole at x equals 0 because you're dividing by x. So to do this, right, we're going to do a change of variables, right? We're going to let n equal ax, right? Keep in mind that as x goes to 0, n also goes to 0. So since it's 0, 0, we're good. So you're going to get sine of n over and n over a, because you have to do x, you got to rearrange this, right? So then you can do that. You can plop out the a because it doesn't depend on x. And I realized that I forgot to change my variable here. So this should be an n, that should be an n, and that should be an n. But a doesn't depend on n, so you can plop that out. And then we know what the limit of sine of n over n is. That is 1 as n goes to 0. So we just get a. So if you change the frequency or the period of your sine function, and you divide, and you have it in this form, you just get a for your limit. So that's pretty cool. What if you have sine of x over the square root of x? Well, we're going to multiply by square root of x over square root of x. Again, that's 1, right? So you can do this. That's just a fancy way of writing 1. And then what we can do is that we can use the multiplication rule for limits to make it the limit of the square root of x. And this one, this limit does go to 0, and this should be x, not z. So again, another typo, my bad. I gotta be more careful in proofreading these now. And then this limit goes to 0. That goes to, wait, what in the world am I doing? Hang on. Sorry, guys. This goes to 1. And then this variable should be x, but this goes to 0. So since we're doing 0 times 1, we just get out of 0. So yeah, so that's all I have to show you for limits. Again, right, there's more advanced things that you can do for limits, right? But if you want to learn more advanced techniques or whatnot, you can look them up. You can go take calculus class, whatnot. But again, physicists, we evaluate limits on a case-by-case basis. So, here we're going to do some derivative examples. So here we got arc cosine, which is equal to cosine inverse. We want to find what the derivative of arc cosine is. So in order to do that, we're going to set y is equal to arc cosine. And then we take, and then we want to solve for x, okay? So we get cosine of y. The reason why we do this is because we know what the derivative of cosine y is. That's negative sine y. But we know that y is dependent on x. So we get, so we have to throw in our y prime. We have to implicitly differentiate this. We take the derivative of x with respect to x. We get 1. And so then you can rearrange to get your y prime over there. We then get sine y in the bottom. We're going to use the identity that sine squared plus cosine squared is equal to 1. We're going to rearrange that. So we can then use that fact to get down here. right? And then we can also recognize that x is equal to cosine of y, and so we get -1 over the square root of 1 minus x squared as the derivative of arc cosine. Okay. You can do a similar sort of thing for arc sine if you wanted to. And then over here, we have an extension of the chain rule. What happens if we have a composite of 3 functions, right? Instead of just 2. Well, what you want to do is you want to turn it into a 2-dimensional. You want to turn it into a two chain rule. I guess I don't know what the best way to describe it is, right? But what you want to do, right, is that, okay, we got k of f of g of x. Well, let's just turn it into k of g of x, right? We can define j of x to be f of g of x. Okay, so then we can do the chain rule like normal, right? We can do dh so we can do the outer with respect to the inner, and then the inner with respect to the variable. Okay, but we don't know how to evaluate this, right? Because j is a composite of f and g. So we go down here, we apply the chain rule again. And then we can plug this in for this, and you get a nice honky log expression of things that has 3 terms in it. So yeah, that's cool, right? And keep in mind, right, is if you go and cancel out things, right, you end up with a dh dx, right? So, well, technically not 100% mathematically sound, to just cancel out those numerators and denominators. It works for us physicists. It gets the job done. So there you go. So here we actually have a little bit more of a physics example. So we have the black body radiation law. Is given by rho of lambda t is equal to 8 pi hc over lambda to the 5th times 1 over an exponential to some goop, minus 1. And the Wien displacement law says that lambda max times t is equal to a constant. Okay, and you want to show that this constant right here is equal to hc over 4.965 times k sub b. Okay, right. If you're familiar with some physics, right, you got pi, you got h, which is Planck's constant, you got c, which is the speed of light, you got lambda, which is wavelength, you got t, which is temperature, k sub b is Boltzmann's constant. So yeah. You can do this by hand. But I don't want to do that, right? Again, this is I'm going to put a note about Mathematica here, right? You know, when you're in your introductory calculus class, right, and you're just starting out, right, it's important to do things by hand so you get used to the process, right, and you understand the theory and what's going on, right? But at some point, you'll kind of cross the threshold where it's like, you know what, you've done it before. We trust that you know how to do it again. So we're just going to allow you to use the computer to get you there, right? And, you know, I've been doing physics. I've been doing physics for a long time, sort of. I mean, compared to some of the professors out there, I haven't been doing physics like at all. But compared to some of you watching, I've been doing physics for a long time. So, so in college, right? You know, by the time I got to my sophomore, junior year, right? They're like, go ahead, you can use the computer, right? Just make sure that you print out the code that you use and submit it with your homework assignment so that, you know, so that way you're still showing your work, right? So what we're going to do here, right, we're going to set y equal to this big, huge thing. Same expression as right here. And we're going to take the derivative of that with respect to L, okay? I used L for lambda, so L is equal to lambda. Right, it can be annoying to type in lambda and some of these Greek symbols into Mathematica. You have to like pull up in the menu and whatnot. So just, you know, just use a different symbol, right? And so we get out a big, huge yikes expression. Definitely a yikes. If you had to do this by hand, yeah, I would not. I would not want to do this by hand. It would take me probably an hour. So I don't think you want to sit here for an hour watching me go through steps. So we're doing this. If you want to do it by hand, go ahead and try it. But there we go. So the maximum point is going to occur when the derivative is equal to 0. Now I know that you're like, well, what about using like the second derivative test to prove that it's a maximum or whatever? I've seen this function before, and I can tell you that there is no minimums. So yeah, it's going to be a maximum, and we're going to roll with it, okay? So we solve for that, right? And so we get L is equal to this thing, okay? First thing you want to realize is that this CH is this HC, and that you can factor out the KT, okay? So you can factor out the KT, right? Keep in mind that since we have a T right here, right, that allows us to just cancel out these T's, and it leaves us with a KB on the bottom, okay? So that leaves us with, you gotta get this constant, okay? So we factored out our KTs, we ignore our CHs, right? And I asked Mathematica to numerically approximate whatever this 5 plus this product log thing is. I tried Googling what product log was, and the best I could gather was that it has something to do with like imaginary numbers and treating them as like reals or something like that. But since we don't have any imaginary numbers in here, I'm not entirely sure why it did it. Yeah, I'm not entirely sure why it did it. But anyway, if you numerically approximate this, you get 4.965, which is our constant. So, bam. That means we did it. That means we must have done something right. So yeah, just a little more of a physics example, right? Of using derivatives. Again, not a problem I would want to do by hand, but you know, sometimes you gotta do what you gotta do. Sometimes you have to do it by hand if that's what your teacher or professor wants. Sometimes you can be doing problems quote unquote for fun, and you can, you know, take shortcuts and trust yourself that you know how to do things by hand, and yeah. So then we have a couple of example problems for series. I think we actually only have the one. Yeah, we only have the one problem here for series. But that is the idea that you can take the derivative of a series. This does also apply to integrals as well, but you can take the derivative of a series, and you can get a function, and then you can get that, and if that series is approximates a function, well then it's that function. So we're going to show that the derivative of sine of x is equal to cosine x by using its Maclaurin series. So this is the formal definition of the sine of x series, right, with an infinite sum, right? If you look at the first few terms, you get this. So what we're going to do is we're going to take the derivative with respect to x, right? So first thing you need to notice, there's no x dependency. That's a constant, okay? No x dependency. That's a constant. X. There's our x. Okay. Well, this is x to some constant. So guess what we get to use? We get to use the power rule. So cool. So we drop down our 2k plus 1. We subtract 1. We get 2k. We leave our constant out here. And then I expanded out the first couple terms of this factorial, right? If you don't remember what a factorial is, look it up. But the idea is, right, is that you can cancel out these 2k plus 1s, and you get out this. And it turns out that that is equal to cosine of x. So that is cool, is that you can take the derivative of a series, and you can show, and then if you can show that series is the same series as another function, well, the derivative of that function is that other function that you just found. So yeah, it's just a neat theoretical thing. But yeah, like I said, I don't have very many example problems. I don't have very many example problems for this one. So like I said before, right, if you want more practice, if you want more repetition, either take a calculus class or you can go online, you can find more examples of derivatives and whatnot. So that being said, thanks for watching. Feel free to like, comment, and subscribe if you enjoyed the video and you found this helpful. If you have questions, if you have feedback, if you think I made a mistake that I didn't catch and you think it's important for me to mention to other people, feel free to email me, or you can leave a comment as well. Thanks again for watching, and I will see you in the next episode.